right? So it's the isomorphism idea. We have said that two groups might be quite different from each other mathematically, but they may still be isomorphic. So one common example of groups that we see is something called a cyclic group, right? It first of all defines what we call as the integers modulo n. If you just consider the set of integers from 0 to n minus 1 with modulo n addition, right? So this Zn is therefore a group, right? So you have a group of n elements, right? So sometimes the addition is shown with a plus sign like that, but in any case, I'm just going to use just plus in here. So that's the modulo n addition. In any case, so therefore this Zn together with this plus operation is a group. Like 0 is the identity, 0 is identity. So the inverse of k is equal to minus k, but that's basically equivalent to n minus k actually, right? Something like that. So the inverse of 1 is n minus 1 because, for example, 1 plus n minus 1 is equal to 0 modulo n, things like that, right? So with modulo n arithmetic, with addition, this set is a group. So the order of the group is the number of elements in it, number of elements. This is usually shown by this absolute value symbol. I'm going to start using this from time to time. So in that case, the order of the group is n, right? Including 0. There are n elements within that group. Okay, so that's one group. So in a moment, I'm going to talk about another group called the nth roots of unity. So here I'm using UN symbol for that. Basically, these are complex numbers where the nth power is equal to 1, right? Or you can think of this as the roots of the polynomial equation z to the n minus 1 is equal to 0, right? So in any case, in complex algebra, there's something called the unit circle in here, unit circle, right? Sorry. On the unit circle, the points on the unit circle correspond to some complex numbers. So if that angle is theta, then that complex number is e to the I theta. So it has a real part, which is cosine theta, and imaginary part, which is sine theta. You can just think about them. So the nth power, so this is really an exponential. So the nth power of this thing is equal to e to the I n theta. Okay. So basically, the nth power is equal to 1 if n theta is basically equal to 0 modulo 2 pi, if you want, right? So if n theta is a multiple of 2 pi, in that case, you get a root of unity. So the simplest root of unity is 1, obviously. 1 to the n is equal to 1. But the next one is e to the 2 pi I over n. All right, because if I take the nth power of this thing, I'm going to get e to the 2 pi I. So e to the 2 pi I over n to the power n is equal to e to the 2 pi I. So that's equal to 1 because of this decomposition in here. And so on, right? We can write e to the 4 pi I over n and so on. The last one is n minus 1 times 2 pi I over n. Right? I mean, let's just divide these two parts from each other. So if I call this number gamma, for example, then this is basically gamma squared up until gamma to the power n minus 1. Okay. So these are numbers of the form e to the 2 pi I over n times k, where k ranges from 0, 1 to n minus 1. Okay, so what's that's basically gamma to the power k, right? So what happens in here is there is some kind of an association in here that sends k to gamma to the power k, but in such a way that, for example, n is sent into gamma to the power n, which is equal to 1. And so as a result, this is like the modular arithmetic that we have discussed in here. So there is some kind of a mapping between Zn and the roots of unity. And this mapping is basically like that. So that means, like, for example, I don't know, if we have some kind of an addition operation in here, like k plus k prime is equal to k double prime, right? If that's like that, modulo n, let's say, then this basically tells us that gamma to the k multiplied with gamma to the k prime is equal to gamma to the k double prime. Okay, so that means these two groups are actually isomorphic. They are more or less the same group, right? Except that, well, mathematically they are different. So we have sets of integers in here. We have some complex numbers in here. We have addition for that group. We have multiplication for that group, right? So this is also an example of a group where I can consider an addition operation as some kind of a multiplication operation too. So as a result, from now on, I'm going to assume that all the groups are multiplicative groups. I mean, naturally, you would think that, for example, translation group is, for example, some kind of an additive group. Well, addition is the operation in that, it's the vector addition. But you can also think of this as some kind of a multiplicative group. The reason why I'm doing this, I need to have some kind of a uniform notation for everything. So as a result, from that perspective, I'm going to assume that my group is a group where the operation is a multiplication. And so as a result, from now on, I'm not going to show any group operation, except in very special places. I'm not going to use any separate symbol for group operation. I'm just going to assume that it's a multiplication, actually. I'm using this kind of an argument that every additive group is somehow isomorphic to a multiplicative group of some sort. And so as a result, since they have the same structure, I can concentrate on the multiplicative one. Okay. There's another group. So that's mathematically something like that. So first of all, let's just, I mean, if G is an element of the group, so just think of it like this. G operation with G, I'm going to think of this as G squared, right? G product, I mean, this is basically a group operation. So probably there's some kind of a composition or something like that in here. So G operation with itself is, I'm going to call G squared, and G operation with, or product with itself 3 times, I'm going to call this as G cube and so on. Right? So in that way, I can define the nth power of an element G. Right? So that's n times. So that's a common notation that we are going to use. And also, I'm going to use G to the minus 1. That's basically inverse as the same thing as minus 1th power. Power of G. Okay. In that case, as a result, I can basically think of G to the minus 3, for example, as the same thing as the cube of the inverse, for example, or the inverse of G cube, right? So they are actually the same. All of them satisfies this property, right? So the G to the n. So there's one last thing, sorry about this. I'm also going to define G to the 0 as identity. Right, that's identity. So together with these definitions, we basically have this. So G to the n is well defined for any integer n. So n can be anything. So any negative number, 0 or a positive number, doesn't matter. So we can define a power. These powers satisfy these properties. So if you have the product of nth and the nth power, So we get that's basically equivalent to n plus m power. And the power of nth power of g to the n is the same thing as gnm, right? So these properties hold true. Okay. In any case, so if we have a group, if we have an element, right? Suppose a group has an element G whose nth power is identity. So let's say G to the power n, that's equal to identity. I mean, for finite groups, there is always such a number. So that's something that is also discussed in the notes as a result. I'm not going to repeat it in here. But for a finite group, all the elements satisfy this, this property, actually. But let's suppose that there's some kind of an abstract element in here whose n power is identity and whose smaller powers are different from identity. So if none of the smaller powers is identity, then I'm going to call this as Cn. So the set of elements which includes identity G, basically all powers of G up until the n minus 1th power is a group. Okay. Is a group where basically you have this property, like G to the K multiplied with G to the K prime is equal to G to the K plus K prime. But in here, I can do a modulo n arithmetic because the nth power is equal to 0, right? G to the n is basically the same thing as G to the 0. They both give the identity. So in that respect, this group is actually isomorphic to Zn. So this Cn is called the cyclic group, right? And this is the common notation that the mathematicians use. So what is that element in here? Mathematically, we don't care, right? Mathematicians basically define it abstractly like that. So it's basically a group generated by an element with satisfying that property, right? So they just define it abstractly. So therefore, this group is also isomorphic to all of these groups. They are essentially the same. There is one more group in here. It's basically, it's not the symmetric group of an n-gon, but think about these rotation operations, right? Rotations in 2D. So each rotation operation can actually be considered as some kind of a transformation where a vector is transformed into another vector, and something like that, V prime. So V is mapped into V prime. So this is actually some kind of a linear map. I can think of this as a transformation of the coordinates, actually. So the V vector has a coordinate. So you actually transform this to another vector where the coordinates, X and the Y coordinates are different, but they are related to the old coordinates by some kind of a transformation. So we have a transformation matrix in here. I'm just going to keep this short. I'm just going to say that I'll talk about this later. This transformation, for example, matrix is actually given by this. So that's the rotation matrix, R theta. So R theta in here, which is a 2 by 2 matrix, corresponds to rotation by angle theta. Okay. And in here, we can, I mean, this rotation matrices satisfy these properties like R theta. I mean, the two rotations followed by two rotations with angles theta and phi, followed after another is equivalent to a single rotation with angle theta plus phi. And then a rotation by an angle of 2 pi is the same thing as a rotation by 0, where the corresponding matrix is 1, identity, right? I mean, there are these kind of things that can be shown. What I'm going to argue in here is that there is actually a set of rotations in here. The first one is identity. The second one is a rotation by 2 pi over n. The second one is a rotation by twice the 2 pi over n multiplied with 2, but instead I'm going to show it with the square of that thing in here, and so on, right? It's basically rotations by 2 pi over n repeated k times, right, in general. So this is also a similar kind of a cyclic group. So let's just call this as C prime n. So in that case, there's also a generating element in here. Let's call this as R. And then we have the square and the cubes and so on, up until the n minus 1 power of the that rotation matrix. All right. So this is exactly how the cyclic group is defined, except that in here, the element is an operation in the two-dimensional plane. Right? It's some kind of a rotation operation in the two-dimensional plane. So here we have a symmetric group, actually, clear symmetric group. That is also isomorphic to all the groups that we have mentioned. Right? Again, let's just start the same thing again. I mean, there are some kind of similarities between all of them. But in any case, so mathematicians usually define the cyclic group in the abstract way. Physicists usually describe the cyclic group Cn. When they call it Cn, actually, they actually mean this group, the rotation group, actually, right? So that's the common notation. There are also some alternative notations which are quite similar to this. But when we say Cn, it's basically this rotational symmetry group. Okay. But again, just keep in mind that the same group appears in different ways mathematically, but they are really the same group actually. If you just consider them in some kind of an abstract way, they are the same group. So in group theory, when we talk about the structure of the group, we are actually talking about the common properties of all of these different looking groups. So as a result, I'll be basically talking about like isomorphic groups are essentially the same group, right? So that's kind of a nice example in here. Okay. Then there are these concepts in here. I don't know if you have any questions at this point. I think this is something that I need to stress on. Because when we talk about symmetric groups, there are some symmetry operations that correspond to something that, but these are usually in our imaginations. We implement them in different ways in physical applications usually. And so as a result, I would like to distinguish this abstract sense of the symmetry operation and the concrete sense of how you implement them in your equations. So I would like to think of this abstract group in an abstract way, basically. So in that case, I don't care how you define the group. What's important is the problem, for example, the multiplication label or some other structures within the group, right? So in any case, we have G is a group, let's say. Let's say G is an element of the group, all right? So let's just form the infinite sequence. You start with the 0th power identity. Take G squared, G cubed, and so on. I mean, take all the possible powers, right? You don't need to start with identity. You may actually start with minus infinity, for example. We can also think about the negative powers as well, but you don't have to think about this like this in here. So in any case, so one of the questions is like, is there a repeated element in here? So is there a repetition, right? A repetition. Yeah, I couldn't write repetition. I mean, are there some elements in here like the kth power and the L power? Are they equal to each other? Right? There are different situations. So if there are no repetitions, for example, in that case, I mean, the group must be infinite because all of these are elements of the group. Right? If the group is G is a finite group, then there must be repetitions. I think I'm trying to explain this in the longest possible way. So as a result, in here we can find like a kth power, which is equal to the L power. In this expression, for example, if I multiply it with G to the minus K, both sides, so we get identity in here and the L minus K power in here. So this then implies that there's some kind of an n where the nth power is equal to identity. So that means like if there's a repetition in here, then somewhere in here there has to be an identity, right? So therefore, this identity is also repeated somewhere in here. Okay. So in any case, the smallest positive n, smallest positive n for which G to the n is equal to identity is satisfied is called the order of the group, order of the element, sorry about this, order of the element. So we have like these two concepts. Order of a group is the number of elements within the group, but order of an element is this quantity here. It is positive, so therefore it cannot be zero. So the zero power is also equal to identity, but that's not counted. So the smallest possible value solution of that equation anyway. Okay. So if that's the case, in that case, identity G, the second power of G, and so on, up until n minus 1 power on G. So all of these elements are distinct. All are distinct. Okay. Why? Because if two elements are the same in here, I can actually use the same kind of an argument, right? G to the K is equal to G to the L, where K and L are both smaller than n minus 1 or smaller than n, which then implies that their difference is equal to identity. So that means that this has a solution which is smaller than n, and so on. Things like that, all right? So because of these kind of arguments, you can show that all of these elements must be distinct from each other. Okay, so in that case, I mean, this sequence, for example, is basically a periodic sequence, right? I mean, if I continue this power in here, so the nth power is going to give me the identity, n plus 1th power is going to give me G, and so on, and G to the n minus 1 in here, and then the 2nth power is going to give me identity, and so on, right? Just think of it like this. So let me try to say it like that. So that's the nth power. That's the n plus 1, n plus 1st power, and so on. So that's like, this is 2n plus 1st power, and so on. Okay. So yeah, we have an infinite sequence in here, but this infinite sequence is repeated periodically. Any questions up to now? All right. Let's see. So, all right. So there are these concepts that we actually use a lot. But I'm not going to go into details in here. So please read the textbook. I think the second chapter, I think everything is explained. It's actually better in there. So probably you don't even have to look at the past lecture videos for this. So if you have a group, right? H is a subset of G, right, is called a subgroup of G if H is itself a group. Okay. So this essentially implies that you can show that in here. So identity is an element of the subgroup, right? If H is a subgroup, a subset of the group is a subgroup, you can use this pictorially like that, right? H is some sub element, subset. So the identity must be in there, right? So that's the first thing. The second thing is that, like, if G is in H, in that case, the inverse also should be in H, right? Because I know that, for example, if every element within the group should have also an inverse within the group. So therefore, the inverse of every element within H should be also in H as well. And number three, so if G and K are in H, this then implies that G times K is in H as well. So their product is also in H. Okay. So as a result, for a subset to be grouped, all of these three properties should be satisfied. So mathematicians usually express this in some simpler way. I mean, they can write down all these three conditions in terms of a single condition. So I'm not going to talk about these actually. So let's say G is a group. And G is an element of the group. And let's say that N is the order of that element. Right? In that case, this implies that the powers of this element, which is essentially all the powers up until the N minus 1, is a subgroup of G. So you can kind of, I mean, this is the simplest group that you can form. Simplest subgroup that you can form. In general, if you have like, I don't know, if you choose some elements within that group, you can then talk about the smallest subgroup generated by all of these elements. Yeah, there's a particular way that we can actually define them, but we don't actually need these kind of things. So we actually need the subgroup concept. All right. If there are two groups, G and K are groups, then there's something called a product group, G and K. Now, mathematically, this is quite hard to describe. If you're not, if you do not understand this mathematical language, perhaps it's hard to understand as well. So for that reason, I don't want to describe it, but please read the notes. So the usefulness of that concept is that sometimes some symmetric groups can actually be considered as the product of two simpler groups. And in that case, analyzing the symmetry might be somewhat easier in these kind of situations. So as a result, I mean, this is one concept that from time to time we actually use. So as a result, just read about this. And also in the exams, sometimes I also ask these kind of things, right? So from two smaller groups, somehow, by using this mathematical operation, we can define new groups. And there are some certain ways where a given group can actually be analyzed, considered as like two subgroups. There's something like that. So I'm just going to call it like this. Let's say M is a group, and G and K are subgroups of M satisfying the following properties, right? since I have entered into this, I'm going to describe this. So the first one is that every subgroup contains identity. So therefore, the intersection of two different subgroups should at least contain identity, right? So the identity is common to all possible subgroups. As a result, if G and K are subgroups of M, then, well, that's basically, they have identity in both of them. So their intersection contains identity. If they don't have any other common elements, then their intersection should be equal to identity, right? So in a way, these two subgroups are different, distinct subgroups from each other. They don't have any common elements except identity, but identity is a common element because it's a common element in all subgroups. So the second thing is like elements of G and K commute. So it's basically something like that. G is an element of G, let's say, and K is an element of K. This then implies that G product with K is the same thing as K product with G. They commute with each other. And number three, every element of the big group can be written as a product of elements of G and K, right? So in mathematics language, so let's say it like this: for any element of the big group, right, we can find elements G in G and K in K such that M can be written as G times K. Okay. In such a situation, that product is unique, actually. I mean, that element in the group, the elements G and K that we are going to find in the groups G and K, they have only a single solution, right? It's something that we can show. If that's the case, in that case, you can show that M is essentially isomorphic to the product of these two groups. Okay. In a way, I mean, this is essentially more or less the product of two groups, basically. You just consider their elements to be different from each other, perhaps only identity are the same, perhaps, all right? But they have distinct elements. They commute with each other, and their all possible products actually produce all possible values of the big product group, actually. So in a way, you can take this as the definition of the product. If you have a difficulty interpreting what this thing is, if you're mathematically minded, you can then just read the notes and then in that case, you can perhaps better have a better understanding of the product. Okay, so I'm not going to say anything about the matrix groups, but I need to say something about the rearrangement lemma. So I have some kind of a notation in here. So let's say, let A be a subset, right? So this is a group. This is any subset, right? And G is any element of the group, right? It doesn't have to be from the subset. And this subset does not have to be a group, right? So A is basically a set where I can kind of enumerate elements like G1 to GR or something like that. So in any case, this is a notation basically. So by notation, for example, G multiplied with A, I actually mean all elements that are obtained, well, a set that's obtained by multiplying all elements of A with G from left, right? And A multiplied with G is the set that you obtain by just multiplying all elements within that set by G from right. So this is actually a convenient notation because at some point we are going to actually use these kind of things, right? So in here, note, right? G, I mean, when I have a listing like that, I actually mean that, for example, these are different from each other. So if I is different than J, then these are actually different from each other. So if these two elements are different, then their product with G from left is also different from each other. Okay, because of some cancellation rule, actually. I mean, if G times Gi is equal to G times Gj, if they are equal, they are not different, right? They are equal to each other. Then I can cancel G's in here, and then I would then conclude that these two are also equal to each other, which is not the case. Right? So in any case, this is also the same for product from the left side as right side as well. In any case, so if these are all different, sorry, I'm going to use a red color like that. So these are all distinct elements. In that case, these are also all distinct, right? Because they can, none of them can be equal to each other. And these are also all distinct. Right, just keep this in mind. There are some certain relationships in here that we can write down. So for example, if I have a product of H with a set that's obtained in this way, for example, that's the same thing as like Hg multiplied with the set. So the associativity rule that is valid with elements is also valid for this kind of notation as well. So that's etc., right? I mean, HAG, so that's the same thing as like, I don't know. This thing is the same thing as HAG and so on. I can write down these kind of things. So let's say that A is equal to A1 to AR. This has R elements. And B is an element, is a set where, yeah, right. So I'm going to use B1 to BS, for example. These are also distinct. So by AB, I mean all the elements that you are going to obtain by multiplying each of the elements of A by each element of B. So as a result, it's like A2, B1, and so on, right? At the end, we have AR, BS. Okay, but in here, some elements might be the same. Some repetitions may occur. Repetitions may occur, right? In that case, the number of elements of AB might be smaller than R times S, right? So number of elements of AB that can be smaller than R times S. So that's a possibility. I don't actually mean that they have to be smaller, but that's something that we need to have. I mean, we need to keep in mind, right? So in that case too, we have things like, I don't know, I mean, ABC is equal to ABC, where the order might be like this, and that's the same thing. Yeah, the associativity also happens in here, right? AG multiplied with B is the same thing as AGB, that with different orders, etc., right? So the associativity holds for these kind of notations as well. In any case, so if G is a group, in that case, G multiplied with G is equal to G. Okay, if I mean, take every element of the group and multiply with every possible element of the group, I basically get all the elements of the group again. But some of them are going to be repeated, for example. So as a result, this is actually a nice example this warning in here, right? In this case, this is the full group, that's the full group, and their product is also the full group as well. So the result is also the same. Okay. So there's something called a rearrangement lemma. It basically says this, right? So G is a group, and G is an element within the group, right? In that case, G multiplied with the group is going to give you the group. There are different ways of actually expressing this. So it can be expressed like that. So suppose that I write down the group like this. So I don't know, let's say that it has n elements like that. So the n is the order of the group. The group. Sometimes people choose this one. The first one is the identity, for example. But that's not really important, right? So the element G is one of these, right? But that's also not important. It can be any one. So what happens is that if I multiply G with all elements of the group, then I'm going to get like G1 in here, G2 product in here, obviously by the definition, right? What I'm saying is that this is actually some element, I don't know, perhaps the ith element in here. But since I'm going to do this for every element, so let's call this like Gi1, right? So G multiplied with G2, so that's an I2th element, and so on. So as a result, this one is going to give me the inth element. So what happens in here is that G multiplied with the kth element of the group is going to give me the ikth element of the group. Right? That's basically what I'm saying. So as a result, there is this kind of a rule in here. Since if the kth element is different than the lth element, in that case, I know that G times GK is also different than G times GL, which means that the element where the kth element is sent is different than the element where the lth element is sent, right? So what I'm saying is that all of these are distinct, and so therefore all of these are distinct. And since the group is the same group, it has n elements. As a result, all of these elements should somehow appear in here, right? That's what I'm saying. Okay, so not only that these are all distinct, since the group has only n elements, all of these elements must be equal to these elements, but they are rearranged, right? So as a result, this is basically equivalent to saying that for left multiplication by G, this is equivalent to, sorry, it is equivalent to a rearrangement of the group elements. I would basically say that this is a permutation of the group element. So left multiplication by a group element is equivalent to, all right, it's just a reordering of, sorry, it's just basically, you get the same elements, but in a different order. That's basically what I'm saying, right? So when people say rearrangement, they're actually meaning this, right? Okay, so the same thing is true for the also for the right multiplication, right? Let me add. Also for, if I multiply all elements within the group from right by that element, so I still get the same elements of the group, but in a different order. Okay, so I'm going to come back to this later, but this is equivalent to what I call as the Sudoku rule. That's my way of actually explaining this. So just think about this group product table. Right? So you just write down identity in here. So they say that this is the first element. You write down second element and so on. Gn in here. And you write down the identity in here and G2 in here and so on. Gn in here. And in here, you just write down the result of these products. So the first row is basically identity multiplied with the group elements. And the first column is 2. All right? Gn in here. G2 multiplied with G2, something, right? I don't know. Let's just call this as Gi, and that's Gj, and so on. Right? We have this kind of a table in here. So what the rearrangement lemma says that in every row in here, every row contains all the group elements, but in a different order. Every row contains all elements of the group, but in a different order. Right? So as a result, identity appears somewhere in here, for example, right? That's what I'm saying. So similarly for the columns. So if you just take this column, for example, or any other column, so that's the true. That's also true for every column. Contains all elements of G, but again, the order just depends. Right? You can actually think of it like this. But the analogy to a permutation, I'm going to talk about it later. Okay, so let me quickly do these other things as well. So rearrangement lemma, we have mentioned about the matrix groups, right? There are actually these topics in here that I don't want to talk about them. One of them is the normal subgroup. Sorry, there's this topic of cosets. I think I'm going to do a short summary perhaps of this one. Well, these are not really needed actually. But these are some basic concepts in group theory. So as a result, it's something that you have to know. And from cosets, for example, you can say that, if, let's say it like this, if H is a subgroup of G, then we can say that the order of the subgroup divides the order of the full group. So you can use this kind of expressions, for example, for analyzing the structure of a group. So for example, I don't know, I mean, if G is a group of order 6, let's say it has 6 elements, this group cannot have a subgroup of order 4, for example, right? Because 4 is not, 6 is not divisible by 4. But it tells you that this group might have a subgroup of order 2 or order 3. You can use these kind of relationships, for example, to analyze the structure of the groups. There's something called a normal subgroup. And quotient groups. This is also complicated, so I don't want to explain it in here. Please read about it. So next week, when I do this, I'm just going to do a summary of this homomorphism. I'm just going to do a quick summary of this, and but I'm not going to repeat the next topic, which is like the conjugacy relationship. All right. So these are some topics that's actually relevant for general group theory. But some of them, we are going to need them. With some concepts, we are going to need them, especially the conjugacy relationship. This is going to be very important for us later. But when time comes, I'm going to repeat them as well. So the result at this point is not, that may not be necessary. So as I said, I mean, These are all topics in the second chapter of the notes that I have distributed. So if you just read that second chapter, then you will catch up with everything. Next week, I'm going to start discussing the permutation groups. And then after that, I'm going to talk about the rotation groups, right? Rotation groups in 2 dimensions and 3 dimensions. So these are going to be my main topics in the next week. So I'm going to finish them by the next week. And starting with the fifth week, I'll start discussing physics. Okay, just keep this in mind. All right, let me finish this.